Okay, so last time we talked about bonding. We talked about drawing Lewis structures. We also talked about resonance structures as well. Remember, resonance structures are when you have a situation where you have more than one option to put the double bond in. You could draw an equivalent Lewis structure for each of those things. So again, we could have, in this case, for example, double bonded to the left. And we could have also double bonded there to the right. And the idea there is the double bond electrons are delocalized, which means they're really kind of hanging around all the oxygens in this particular example here. And at any given time, they could really be at any of the oxygens. So one Lewis structure by itself may not sort of adequately describe what's going on. We also talked about at the end there bond enthalpy, delta H of the reaction, using bond enthalpy. And basically the idea here is when we have a reaction, everybody on the reactant side pretty much needs to be broken in terms of their bonds. So we got to break all those bonds. Then we're going to add it to all the energy that's required to make all the bonds on our product side. Remember that when we do make bonds, it is an endothermic situation. And when we break bonds, it is a exothermic situation. I'm sorry, make bonds is an exothermic situation. And really what you want to do is just kind of count up all the bonds you made, all the bonds you broke. Endothermic will be positive numbers, exothermic will be negative numbers, and you add them together, and that'll give you overall the delta H for the reaction based on bond enthalpy. And again, if you get a negative value, it's an exothermic reaction. If you get a positive value, it's an endothermic reaction. So I think we're in the middle of some of those examples. So let us continue on here. Why don't we try this one here? So let's say we have this reaction here. And using obviously our table here, calculate the delta H for this reaction based on bond enthalpy. So take a few moments there and see what you come up with. Remember that when you're doing this, you may want to draw just quickly a Lewis structure of these things so you could kind of see what bonds you need to make and which bonds you need to break. Yeah. So CH4 plus Cl2, CH3, Cl plus HCl. Okay, so let's take a look. So remember on our reaction side here, we're pretty much going to break all these bonds. And again, on our product side there, we're going to made. We'll go with make. That's kind of like made, I suppose. We're going to make all these bonds over here. And again, if you're not sure what things look like, you may just want to kind of quickly sketch some Lewis structures here. And obviously this is CH4. Cl2 will look something like that. So that's everything that we're going to be breaking. On our product side, if we kind of sketch those guys, we'll have something that looks like this in terms of what we're making. And that's got a Cl. And we always have an HCl as well. So again, good idea to also make sure that you're not dealing, for example, with a double bond or triple bond so that you get the right value, obviously. So clear, if we just kind of count up everything, I got 1, 2, 3, 4 carbon hydrogen bonds that need a break, and each one is 414. That's going to be 4 times 414 kilojoules. I have one chlorine bond that needs to break, which is down here. So that's going to be a 243. For my chlorine bond. And that's going to do it for everything I'm going to break. So that's going to be 4 times 414 plus, and again, we're adding this together, basically all the energy required, 243. It's going to give me an 1899 kilojoules. This again is going to be a positive number because as we break it, it's endothermic gas, put the energy in, so it should be a positive value. On the other side here, on our product side, we're going to actually make 1, 2, 3 carbon hydrogen bonds. So we got to make 3 of those carbon hydrogen bonds. And again, that is going to be 3 times our 414 kilojoules. We are also going to make one carbon-chlorine bond, which is right here that we don't want to miss. And that's going to be 1 times carbon-chlorine, which is, where is that guy there? Right there on the bottom, 339. And lastly, here we have a hydrogen chlorine bond that we need to break, which is right there. 431 looks like. 1 times 431 kilojoules. These are all exothermic, which means technically all these energy values are negatives. And again, we're going to add all those guys up, and that'll give us 3 times 4, 14, plus a 339, and plus a 431. It's going to give us a negative 2012 kilojoules. Now, our delta H at this point for the reaction based on bond enthalpy, we basically just add those numbers together. So positive 1899 kilojoules plus a negative 2012 kilojoules is going to get us there. About a negative, I'll go up here, negative 113 kilojoules in this case, yeah. Question on that calculation. This would mean that this reaction based on bond energy is exothermic, right? We got a negative delta H value, so that would mean that overall, based on bond energy, there's sort of a release of energy as the difference between what we made and what we broke, basically, in terms of bonds. Any questions on that? Now, you can't go like we just did here individually, and it's probably the safest move. Some people will go, well, you broke 4 of these and you made 3 of those. So some people will just say that's a net of 1 that you broke, and that's all you have to worry about. And you could do that as well, since they will kind of cancel each other out. But if not, you could kind of go every single bond so you don't miss anything. Any questions on that there? All right, let's try another one here. That was what we just did. There it is. So why don't you do this one here? H2 plus O2 makes hydrogen peroxide, H2O2. What is delta H based on bond energy of this one? If you're not sure, the oxygens are hooked up to each other and the hydrogens are hooked up to the oxygens. It's refreshing. Okay, let's take a look. So once again, if you're not sure, we're going to, again, break this side. We're going to make this side. So hydrogen does look like this. Oxygen actually is a double bond. So again, if you don't draw the Lewis structure and you think it's single bonded, you will get the wrong value here. And on the making side, a little hydrogen peroxide action is something that looks like this. So in this case, in terms of what we are breaking, we're going to break a hydrogen-hydrogen bond there. So we got 1 times our 436 kilojoules. We are going to take out a double bond here, which is our 498 kilojoules. And that is all we are breaking there. So that's going to get us 436 plus a 498. Looks like a 934 kilojoules. On our making side here, we have 1 oxygen-hydrogen bond there, and we also have 1 more there. So that is 2 of the oxygen-hydrogen bonds, which is right here, 464. This will be negative 464 as we are making it. And again, the bond that sometimes people miss and why it's a good idea to draw it is the bond in the middle there between the oxygen and the oxygen. So we also have that bond as well that we do need to make. So we got 1 of those oxygen-oxygen kind of single bonds happening, which is right there, 142. 142 also going to be negative since we're making. And if we add all that together, so we talked about resonance structures, and again, as we were going through it, anytime where you do have more than one option to move the double bond around, you will do so. And you can draw more than one structure for that particular molecule. And again, we use these arrows here to indicate that we have more than one structure that can happen. Again, a couple of examples as we saw, again, here, ozone, we could move the double bond from the left-hand side to the right-hand side. The charges here are their formal charges actually on each of those elements. Carbonate, which I drew earlier and we, I think, did previously when we were doing Lewis structures, also an example of that. Again, those double bond electrons are really sort of moving around from sort of element to element. As we also talked about, I think, again, you do not need to necessarily draw all the resonance structures unless you're asked to do so. If you drew any one of the three structures, they would be sufficient. A benzene ring we don't deal too much with, but it is an organic compound. Looks something like this. It's actually a 6-carbon ring. Each of these things are carbons. And it has a double bond, 3 double bonds, which could also move around that way. And sometimes the benzene ring is just drawn with a little circle inside to indicate that those double bond electrons are sort of moving around. If you take organic, you'll draw benzene rings all day, but we don't deal too much with it here in this type of chemistry. All right, so we got the idea on that, I think. The last thing we're going to sort of talk about here is exceptions to the octet rule. Although we do want to strive usually to sort of obey the octet rule, there are a number of exceptions to the octet rule that you do need to be aware of, and that does sort of pop up occasionally. The first type of exception to the octet rule is what's known as an incomplete octet. And in an incomplete octet, basically, much like the name implies, it will have less than 8 electrons, and they're perfectly okay with that. Typically, beryllium, aluminum, and boron are your 3 that will kind of do the incomplete octet type of deal. You're sort of deficient in electrons. I would say in most cases, probably boron is going to be the one you're going to see probably the most. But here, beryllium hydride has only 2 4 electrons, is perfectly happy. Boron here has 2 4 6 electrons, and it is also okay in that situation. And like I said, probably those 3, beryllium, aluminum, and boron, although in most cases, boron's probably the one that's going to be involved in sort of covalent bonding in most of the cases. So that is probably your most common sort of incomplete octet that you meet. An incomplete octet like this means that it is electron deficient. It doesn't have 8 electrons. It actually makes it quite reactive in a sense. And if you take 200B, you will see something like this. And this is what is sometimes referred to as a Lewis acid. And a Lewis acid is something that can accept a pair of electrons. And it's able to do that because the boron here doesn't have 8. So it's very easily able to accept a pair of electrons. For example, from something that is considered a Lewis base, like ammonia, that has those pair of electrons, that's a Lewis base, which is something that could donate a pair of electrons. So those 2 guys could hook up very easily because of that deficiency that occurs in the boron. Because of the lack of electrons, it's able to accept those. And it will kind of do that pretty readily because it kind of wants to fix that situation. Again, boron, aluminum, beryllium, kind of your 3 that can go kind of the incomplete sort of octet route. Now, another important exception, or a couple of important exceptions, is these couple here. The next one's an odd electron molecule. These are guys that pretty much when you add up the total number of valence electrons, you get an odd number. And because you get an odd number, that means we're going to have some unpaired electrons happening. And in the case of NO and NO2, that is the example of what happens. You get this unpaired electrons. These are sometimes referred to as like free radicals, you might have heard of. Yeah. Free radicals are quite reactive because, frankly, they only have one electron, so they want to fix that situation. So again, it makes them quite reactive. A lot of chlorine in the atmosphere does sort of free radical sort of chemistry up there, and they have one electron, makes them again quite reactive because they kind of want to fix that situation. And that's an odd electron molecule. Now, probably the exception to the octet rule that we see the most, and definitely that we deal with the most in this class, is this one right here. This is the expanded octet. And much like the incomplete octet, which is less than 8, the expanded octet, much like the name also implies, is more than 8. So there are certain guys that can go over 8 electrons. Some molecules can go beyond 8, upwards of 10 to 12 electrons basically bonded to the central atom. Those that could do that is, if you look on the periodic table, your friend sulfur, and you kind of go to the right, to the left, and down, kind of in the non-metal region. These guys are able to go the expanded octet. That is because sulfur is on what period on the periodic table? Sulfur is on period number 3. There you go. I'll give you props. It was 6. 6 is the group number there, but it is on period number 3. And as we know, that is the n equals 3 level, right? When we talk about electron configuration, that also means on the 3rd energy level, what orbitals are present? There are S's, right? There are P's, and that is the 1st energy level that we see d orbitals present. And because they have those d orbitals present, they have a place to stash the extra electrons, even though they may not be using them. They have the ability to go above 8, again, 10 and 12 electrons, 5 and 6 bonds in certain cases, because of the availability of those d orbitals. That is also why if you go above them on the periodic table, we'll double jeopardy the question. That is period number 2, yes, which means that n is equal to 2, and on the 2nd energy level, there's only s's and p's, no d's available. That means that anybody above them on the periodic table should never, ever go above 8 because they have no way to do that. They can only go to 8, but everybody has sulfur right, left, and down. Really, again, non-metals, even into the sort of noble gases as well, they have that ability to go greater than 8 electrons. So if we look at something like SF6 here, that's going to be 6 plus 6 times 7. That's a lot of math there. 42, 48 electrons we'll go with. That's going to be sulfur in the middle. We're going to F it up all over here. Go. We're going to do our same thing. We're going to do a single bond to everybody. That is 2, 4, 6, 8, 10, 12 electrons. 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, and 48 electrons. Sulfur is perfectly happy with that. And at this point, though, the sulfur has 2, 4, 6, 8, 10, 12 electrons around it. It has 6 electron pairs, and it is perfectly good. I would say probably the expanded octet is the most common one that we see. It is also why, for example, we'll go back this way. That'll work. If you perhaps, looked at something like SO4 2 minus, right? And you had to draw the Lewis structure for it. SO4 2 minus. If you follow our sort of steps, you will end up with this structure here. Again, if you follow sort of our steps and all that good stuff. Now, I'm sure nobody would do this, but if you just Google the answer, perhaps, right? And maybe if you looked online and you Googled it and all that good stuff, and maybe you did this in your previous class and your instructor probably knew you did that, by the way, you might come up with this structure here. By the way, teacher would know you did that because probably in the previous class you didn't do expanded octets and there should be no reason for it to have double bonds on it. So they probably know you just looked it up on the computer. It is perfectly fine in that situation as well. It's a perfectly good structure. Actually, we talked about this as well when we talked about formal charge, right? So if we did our formal charge, for example, on our single bonded oxygen, that would be 6 minus 6 minus 1/2 of 2 is a -1, right? So that's again valence electrons in the atom, number of non-bonding electrons, half the number of bonding electrons. That would give me a -1, -1, -1, -1. And if I did my sulfur, which looks like this, that would be 6 minus 0, as there's no dots, minus 1/2 of 8. And that's going to give me a +2 happening there in terms of this structure for our sulfur. We add all that together, it's +2 in the middle, -4 on the outside. That's a -2 overall, which equals the charge, which is all good. Now, if I did the formal charge for the bottom structure, which you might have Googled, you would end up with obviously the same for our single bond, 6 minus 6 minus 1/2 of 2 gives you a -1. So we have -1, -1. We would have a double bonded oxygen as well, which would be 6 minus 4 for our non-bonding electrons, minus 1/2 of 4, which is 0. And now for our sulfur, which would then end up looking like this in that second structure, that's going to be 6 minus 0 minus 1/2 of 2, 4, 6, 8, 10, 12, which will give me 0. Based on formal charge, which is actually the better structure. In this case, it actually is the Google one that's the better structure in this case, even though you shouldn't have ended up that way. So if you were drawing this based on formal charge, this one actually is a better structure, which is why it's on the internet, because it minimizes the formal charge, obviously, to the zeros and -1s. But if you just follow the regular rules of sort of drawing a Lewis structure, you would end up with the top one. Again, this is a situation like we talked about. You could use formal charge if you wanted to pick between structures and maybe pick a better structure based on formal charge than another. Any questions on that there? Yeah. Okay. All right, so let's draw some expanded octets here. So why don't you give those guys a go? Draw each of those Lewis structures and see what you come up with here. 8 plus 4 times 7. And that is, dare I try the math here, that's 36, I think, 28, and 8 is 36. We're gonna go xenon in the middle, fluorine around here. Again, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So here we go. We now have 8 times 4 is 32. We have 4 more electrons to go. So we're going to put those on the central atom in this case here. Any questions on drawing the expanded octet? Assuming you hit the right number there, I suppose. They'll put extra electrons that they don't need. So you really just want to follow the same rules as we talked about for drawing regular sort of Lewis structures. Again, sulfur left, right, down has the ability to go above. And as I mentioned earlier, above sulfur on the periodic table, you should not go above. Any questions on any of that there? All right, so chapter 4, truthfully, is just a continuation of basically what we've been talking about. So we've talked about obviously drawing Lewis structures, expanded structures, bond polarity. Here in this chapter, we're going to cover molecular geometry. We're also going to cover molecular polarity, and we're going to talk about some hybridization models and stuff of that, of bonding. So kind of a continuation here. So let's start with geometry. When we talk about molecular geometry, it does refer to the three-dimensional sort of arrangement of obviously the atoms and the molecules. The molecular geometry cannot be predicted by necessarily the Lewis structures, but if you know basically how many electron pairs there are around the central atom and how many bonds there are, which from a good Lewis structure you'd be able to determine, you will be able to predict is sort of molecular geometry. And when we talk about geometry, we're actually going to talk about two types of geometry and two types of names. One is going to be referred to as the electron pair geometry. Which for my purposes here, I'm just going to abbreviate EP for electron pair. The other one is the molecular geometry. And sometimes people just refer to this as the shape. And for our purposes here in this lecture, I might just refer to it as MG for molecular geometry. These are names that describe, as we will talk about, pretty much how the electrons are arranged around the central atom in terms of electron pair geometry, and the name for the molecular geometry talks about the overall shape that takes into account how many electron pairs there are, what types of electron pairs, what types of bonds are present in these things. As we will see in certain cases, these names will be the same, and in other cases, they will be some different names that occurs because of the types of electrons that are present. Now, the best approach that we take is, or the approach that we do take here, is the idea that we are dealing with electrons which are negatively charged. And when you're making bonds and you got electrons around everything, do they really want to be near each other since they're all negatively charged? They actually do not want to be near each other because things that have the same type of charge really are repelled by each other. The problem is they can't really escape because, frankly, they're in a bond and the other electrons are stuck onto it by the attractive force to the nucleus. So what ends up happening in this sort of model is the electrons really, in all cases, will try to get as far away as possible from each other. Again, they can't really escape because they got to hang on there because they're bonded. So they'll start trying to move away as far as possible from each other. And what that ends up doing, if you just think about it, if you have a bonding pair of electrons, as those bonding pair of electrons start to move, so does the atoms that are connected with those bonds, right? They start to move with them. If you have non-bonding electrons, they will start to move. And as those non-bonding electrons get near something like bonding electrons, they're going to try to get away from each other as far as possible. And that ends up causing the actual shape of the molecule to really change, depending on really, as we'll talk about, are there bonding electrons present? Are there non-bonding electrons present? Is there a little bit of everybody present? And depending on those type of electrons, everybody will really try to keep moving so they could kind of go, all right, I'm okay with it, and lock themselves into place. So that's how we get to sort of different names and different sort of geometry for these molecules as they're trying to kind of move around. All that is also energy based to move around to minimize energy as they're doing that, by the way, to kind of bring down the overall energy aspect of it as well. So this theory is what's known as VSEPR, which is known as the valence shell electron pair repulsion model, hence the abbreviation. That is a long name. And when we do this type of geometry here, we really will sort of look at molecules that are broken up into kind of two categories. Categories where the central atom does not have lone pairs. So basically, if you draw your Lewis structure, there's no dots basically around the central atom. And we will have ones where the central atom does have lone pairs. So when you draw your Lewis structure, you'll have some dots perhaps around the central atom. Now, when we do geometry, it's really important, two things really, and these are the two things really that you want to count when you're trying to do geometry. because most people, frankly, can't visualize three-dimensional space in their head and what things look like as things are moving. So really the things that you want to look at is when you're doing geometry, if there is a central atom, you always want to look at the central atom. It is the most important element, if you will, or atom in terms of the geometry. If you happen to have multiple central atoms, you would actually want to look at multiple central atoms. But if you just have one, you would look at the central atom. And you want to count two things. You want to count up basically the number of electron pairs there are. And this does not matter of whether they are bonding electrons or non-bonding electrons. It doesn't really matter. And you also want to know how many bonds there are. Also, doesn't matter if it's single, double, or triple bonded. So when you're doing geometry, and only when you're doing geometry, anytime you go to count up electron pairs, if you have a single bond, if you have a double bond, if you have a triple bond, it does not matter. They're all counted the same. They all count as one. So if you have a single bond, a double bond, or a triple bond, that counts as one electron pair. Because in a double bond or triple bond, they're effectively working together as one electron pair. So when you're doing geometry, you count them all as ones. And the same thing with the bonds, whether it's a single, double, or triple, everything counts as one, basically. So that is, again, strictly, obviously, when you're doing geometry, you're doing this sort of geometry model, everybody counts as one. The other sort of consideration is not super important, but it is, I guess. If you are drawing multiple resonance structures, you pretty much could do this geometry for all the resonance structures that you draw. And in most cases, all the resonance structures will hit the same geometry because they're basically just a double bond kind of moving around in most cases. So they'll hit pretty much the same geometry if you did it for all three resonance structures, or if you just did it sort of the geometry for one. So let's get going on some of this geometry here. And let's really just start with the simplest arrangement you could have. And frankly, the simplest arrangement you could have is a diatomic molecule. And in a diatomic molecule, there really is no central atom because, frankly, there's just two. There's just two atoms present, which makes it diatomic. And in a diatomic molecule, because there's no central atom and because you only have two things, the old saying is the shortest distance between 2 points is a straight line. Yeah. So the only way that you could arrange the geometry of those two things is they are connected by a straight line. No matter where you put it, they're just going to be straight line from each other. So the geometry of any diatomic molecule, you should just put linear and move on with your life. It doesn't matter. Doesn't matter if it's a single bond. Doesn't matter if it's a single bond in different things. Doesn't matter if it's a double bond. Doesn't matter if it's a triple bond. All these guys, the geometry for all these guys are linear, and that's just what it is. Again, two things, diatomic molecule, two of the same, two different, single, double, triple, doesn't really matter. The only way you could arrange those things is in a straight line, basically, and the geometry is always going to be linear. Any questions on that? Now, clearly, when we get to what we're going to talk about next, which is three or more atoms, you always want to look at the central atom. So when you get the three or more atoms, it is always the central atom that is the most important. Who cares about anybody else? Again, if you have more than one central atom, we'll talk about towards the end. But if you have one central atom, that is the most important. So, for example, if we take a look at this guy right here, incomplete octet and all, our beryllium is our central atom. We're going to count up the electron pairs. So that is one electron pair, two electron pairs. So number of electron pairs is 2. Number of bonds would be 1 bond, 2 bonds is 2. Now, something with 2 electron pairs, the electron pair geometry will be linear. What's going to happen is everybody's going to just go as far away as possible from each other on opposite sides, basically. And that gets those electron pairs as far as possible. Because these are bonded atoms, as those electrons move, so does my chlorines in this case also moves to the opposite side of each other. And what that gives us for the molecular geometry or the shape name is also going to be linear, 180-degree bond angle. They basically can move themselves as far away as possible from each other and be happy in that situation. They're not like right next to each other, and we get this linear. So the electron pair geometry name is linear in this situation when you have two electron pairs. That geometry is really based on the number of electron pairs you have around the central atom. Two electron pairs in combination with two bonds will give you your linear geometry for the molecular shape. Next geometry is one where we got a central atom and three things attached, like in boron trifluoride. This is also an incomplete octet. If we take a look at our central atom, we got 1, 2, 3 electron pairs. We also have 1, 2, 3 bonds. Once again, something with 3 electron pairs. The electron pair geometry is going to be what is known as trigonal planar, also sometimes referred to as triangular. It is triangular because what's going to happen now is those electron pairs are going to start to move. And as those electron pairs start to move, these two guys can only get so close to each other, but they also need to now keep, because we have the third bond there, the distance to the top guy. So the guy kind of spread out. And what they end up doing because of that, once again here, these are all bonding electrons. So as these electrons move, so does our atoms move with it. And that will give us a molecular geometry or shape, also known as trigonal planar. And that is because it pretty much makes a triangle. A nice little triangle is made basically in this geometry here. Bond angle here is 120 degrees. And again, the bond angle does go with really the electron pair geometry in the trigonal planar here. So when we add the sort of third bond there, we have an extra set of electrons that everybody's got to kind of keep distance from. So they can't just spread out like they did with the two. They kind of move down a little bit to make room for the guy up on top. And again, it allows them to kind of keep the equal distance from each other. Any questions on that one there? Continuing on here, we got something with three central atom with 4 things attached in this case. And in this case here, we're going to look at the carbon. Carbon's got 1 bond, 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. Number of electron pairs in this case is 4. Something with 4 electron pairs, the electron pair geometry is tetrahedral. Or tetrahedron if you find an old book laying around. With that, it also has 1, 2, 3, 4 bonds. Again, here, these are all bonded electrons. So as they move around, we now have an extra set of electrons in the way. So again, they cannot get like super close to everybody. They got to keep some distance happening here. And this is going to give us a molecular geometry also known as tetrahedral in this case. In this case, we have a bond angle of 109.5. And again, they're going to now have that 4th sort of bond in there. Doesn't allow them to fully get away from each other. They got to kind of come in a little bit at all spots. And it kind of makes like a triangle on the face, little pyramid sort of action-ish on the bottom in terms of its tetrahedral arrangement. These are probably geometries that you're familiar with. Let's talk about maybe some that you don't, which go with our friends, the expanded octet. And that one's going to be this situation here. This is a situation where if we look at our Lewis structure here and our central atom, we have 1 electron pair, 2 electron pairs, 3 electron pairs, 4 electron pairs, and 5 electron pairs. This is basically an expanded octet. Something with 5 electron pairs has an electron pair geometry known as triangular, bipyramidal. Once again, if we count up the bonds, we got 1, 2, 3, 4, 5 bonds. That also creates a 5th sort of electron pair in the way, which is bonding. And that's going to give us a molecular geometry also of triangular bipyramidal. This actually has 2 bond angles that occur. We got a nice 90-degree happening right about there. And we have a triangle happening right about there, like our trigonal planar situation, which is our 120 degrees basically happening right about there. So this one actually has 2 different bond angles, a 90 and a 120 happening here. This again is an expanded octet, triangle bipyramidal molecular geometry and electron pair geometry in this particular case. Questions on that one there. Now, another expanded octet geometry, which will probably be new to you, is one where we go with 6 electron pairs around the central atom. And when we go with 6 electron pairs around the central atom, like we just drew there with our sulfur hexafluoride, looking here, 1 electron pair, 2 electron pairs, 3, 4, 5, and 6. So number of electron pairs is going to be 6 here. The electron pair geometry name is going to be for 6 octahedral. Our molecular geometry name will be based on how many bonds we have, which in this case is 1, 2, 3, 4, 5, and 6 bonds. And our number of bonds here is going to be 6. The molecular geometry name is also octahedral. We also have, as you can see in this picture, 90-degree bond angle basically happening in this case. So these last 2 are our expanded octets, our triangular bipyramidal with 5 electron pairs, 10 electrons, and our octahedral with 12 electrons, basically, and 6 electron pairs. Question on that. Up until this point, if you look at the electron pair name and the molecular geometry name, are they the same or different? They're all the same. And they're all the same because of the type of electrons there are around the central atom. They're all bonding electrons. Which means as those bonding electrons move, because they're attached to atoms, or the atoms are attached to them, they will move accordingly. They will move in the exact same location. And whenever you draw a Lewis structure where there are no dots on the central atom, no non-bonding electrons, both the electron pair geometry name and the molecular geometry name will always be the same. So if you got all bonding electrons, no lone pairs on the central atom, then the electron pair geometry and the molecular geometry will always be the same. Yeah. And again, because they're basically the same electrons moving the same atoms in the exact same location. It is only when we introduce non-bonding electrons to the central atom that we actually get a difference in the name. And when we add non-bonding electrons, it is the molecular geometry name that actually changes. The electron pair geometry still stays the same because there's still the same number of electrons around it. But because it's a lone pair now and not bonded to an atom, the geometry is able to move a little bit more, the overall molecule, and the molecular geometry or shape is actually the one that changes. So let's take a look at really why this happens and to the degree at which it happens. And it has to do with repulsion types. Sort of the best situation in terms of electrons being near each other is what we just talked about, bonding near bonding, lines near lines. The worst situation to that is non-bonding electrons near bonding electrons, dots near lines, basically. The worst case scenario where they want to get as far away as possible as they can, and they're able to do that because they have less bonded atoms there, is when we have non-bonding electrons near non-bonding electrons. They will try to get as far away as possible from each other. They're able to do that once again because there's less atoms involved, because they're non-bonding electrons, so they're able to move a lot further away from each other. Once again, once we start introducing these guys, the molecular geometry name will change. Once again, the electron pair geometry will still be the same regardless of how many electrons you have. So let's take a look at some of these here for fun. First one we're going to look at is sulfur dioxide. And if we look at sulfur dioxide here, we look at the central atom where the sulfur is, number of electron pairs. It has one here. Double bond counts as how many electron pairs? One. Non-bonding electrons count as one electron pair. So that is 3 electron pairs. Something with 3 electron pairs, the electron pair geometry name is still going to be trigonal planar. But in this case, we only have 1 and 2 bonds. And we have bonding electrons near bonding electrons, non-bonding electrons near bonding electrons. So these guys are going to go and come down, and they can't get too far away from each other. So we're going to get a molecular geometry name of what is known as, I go with angular for a reason. I will say some people go with bent for this one. Some people go with bent angular for this one. For us, we're going to go with strictly angular, and I'll tell you why later on as we go through it, why we don't use bent maybe for it. But just so you know, bent is used for this one. Like in your lab book, they use it. But we'll talk why that is. The bond angle that we got here is less than 120 degrees. So it is based off of the 120-degree bond angle from trigonal planar. But because it has these non-bonding electrons here, it allows the molecule to kind of move a little bit more, and it also affects the bond angle. So it's a little less than 120 degrees in terms of its bond angle. Any question on that one there? Let's take a look at the next example, which is NH3, which you might have done before as well. We take a look at this guy here, central atom. 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. Number of electron pairs is going to be 4. Number of bonds in this case is going to be 3. 1, 2, and 3. Once again, the electron pair geometry name is based on the number of electron pairs, which is 4. That is still tetrahedral. But in this case, we also have bonding near bonding, non-bonding near bonding. So again, with those non-bonding electrons, these guys want to get as far away as possible, but they can't get too far because we have that kind of bond right there. They got to kind of keep their distance from. And we end up with a molecular geometry known as trigonal pyramid or pyramidal, whichever way you like to call it. It has a bond angle also of less than 109.5 degrees. This particular one's actually 107 degrees or so is really the bond angle in this particular case. It is trigonal pyramid because it makes like a triangle and also that pyramidal shape happening there, right, as you go through there. Got kind of like a pyramid on the bottom and a triangle on top. By the way, just a moment here to talk about 2 important names, trigonal pyramid, and we just talked about earlier trigonal planar, which is 3 and 3, right? These are different names. They imply different things that are drawn there. Do not just lay up my favorite answer, which is trigonal, and let me choose, because I will choose with an X, yes? So choose trigonal planar, trigonal pyramid. Don't need to do my other second favorite, which is trigonal. I'm very confident. That's clearly pyramid or planar. Can't you see it? It clearly is that. All right, so make sure you choose. They are different. You can't just write trigonal, so you have to write the rest of it with it. Continuing on here with some electron pairs, our friend water. Now, water here, if we look at the oxygen, which is the central atom, it has 1 electron pair, 2 electron pairs, 3 and 4 electron pairs. It also has 1 and 2 bonds. Something with 4 electron pairs, again, the electron pair geometry name is going to still be tetrahedral. Problem in this situation is we have all of the worst interactions happening at once. We have bonding electrons near bonding. We have non-bonding electrons near bonding, and the worst interaction, which is non-bonding near non-bonding. This has got all 3 of those interactions happening. More importantly, it has those non-bonding electrons, which are just going to try to go as far away as possible. So as those non-bonding electrons spread that way, the bonding guys start to go this way and bend down. And that gives us a molecular geometry known as bent or V-shaped. And this is why for the previous one, we're not going to use bent, because bent actually has a bond angle of less than 109.5 degrees, about 104 in this particular case. And that's why angular has a bond angle closer to 120, a little less than 120. This one's really less than 109.5. So that's why we're going to use the distinction between those two. So 4 electron pairs, 2 bonds will be bent or V-shaped. 3 electron pairs and 2 bonds will be angular, again, so we know exactly which one we're talking about. Any questions on that there? Well, we had some expanded octets, which means that, and as you can see there, 104.5 for water is really what the bond angle is. Those expanded octets also have some non-bonding electron action happening. So let's take a look at this one here. This is a central atom where we have 1, 2, 3, 4, and 5 electron pairs. And we have 1 and 2 bonds. Once again, something with 5 electron pairs. The electron pair geometry name is going to be our triangular bipyramidal. This also has all of the really bad things happening, non-bonding near non-bonding and bonding near bonding. What happens here is all these non-bonding electrons basically fan out in like a triangle type shape, allowing our bonding guys to actually end up opposite of each other. And this will give us a molecular geometry here of linear. This is the expanded linear, by the way, not the linear that we talked about with 2 and 2. That has a bond angle of 180 degrees because they're able to really spread themselves out there at 180 degrees. Any questions on that one there? Continuing on here, we're going to finish out the last geometries here, so we're going to go a little bit over, so just relax. We'll continue on. We'll take a look at another expanded octet here, which is this guy here. We'll look at our central atom. We have 1 electron pair, 2 electron pairs, 3, 4, and 5 electron pairs. We have 1, 2, and 3 bonds. Something with 5 electron pairs is still our triangular bipyramidal. Here again, what's going to happen is our non-bonding electrons are going to come this way, and these guys can't really get too far away from each other because they're trying to escape these guys as well. And this is going to give us a molecular geometry known as T-shaped, because I'm imagining it makes like a T looking symbol there if you flip it upside down, right? So it looks something like that. That T shape is a little less than 90 degrees is the bond angle. Again, a little less than what we see with our triangular bipyramidal here. And we also have like a little less than, it's really more like a 90 degrees. Continuing on here, we're not going to worry about axial positions. These are axial positions which are on the axis, and like the equator going right through the middle are equator positions there. We're not going to worry too much about that. We'll take a look at this one here, which is an electron pair. Our electron pairs there on the central atom of 1, 2, 3, 4, and 5 electron pairs. Here we have 1, 2, 3, 4 bonds. Once again, here are electron pair geometry, still going to be triangular bipyramidal because of the 5 electron pairs that are present. Here again, we have our non-bonding electrons going to kind of go up, going to cause these guys to come down, these guys to keep some distance, and these guys to kind of keep some distance. This is going to give us a molecular geometry known as seesaw. Seesaw. There we go. And seesaw has less than the 120 and 90 degrees, and a little less than that as well. If you come across maybe an older book or something like that, seesaw is also sometimes referred to as a distorted tetrahedral. Old school name, distorted tetrahedral. I would say that most books nowadays roll with seesaw for that name, but if you come across distorted tetrahedral, that's also seesaw basically. So it's kind of the same geometry there. Continuing on with our expanded octet here, we're going to look now at some 6 electron pairs with some non-bonding electrons. So if we look at the central atom here, I think we drew this guy earlier. We have the number of electron pairs is going to be 6 in this case. 1, 2, 3, 4, 5, and 6. Number of bonds is going to be 1, 2, 3, and 4 bonds. So once again, something with 6 electron pairs. Electron pair geometry name is octahedral. We are again going to get our kind of spreading out of everything. These guys can't go too close to each other. They got to also keep some distance here. And it actually ends up with a molecular geometry known as square planar, which is pretty much what it sounds like. It makes a square within the plane of the molecule, basically. You could draw a square right there. Makes a square basically through the bonded atoms that are happening in that case. The non-bonding electrons actually go like almost 180 from each other, away from each other to spread out. In terms of our square planar, because it's a square, that means each of these guys kind of like a 90-degree bond angle sort of happening here with our square planar. So octahedral, 6 electron pairs and 4 bonds gives us square planar. And the last thing that you wanted to hear was the last geometry. Thank goodness, right? It was much better when we didn't expand our octet. Here we're going to look at our central atom. And again, we have 1 electron pair, 2, 3, 4, 5, and 6 electron pairs. That means, again, our electron pair geometry name is going to be octahedral, which is our 6. We're going to get some spreading out here for our molecular geometry, and it's going to end up with the geometry as those electrons move around known as square pyramidal. And as you can imagine, it kind of makes like a square and a pyramid sort of shape happening as you kind of come down there in 3-dimensional space. Our square pyramid is going to be less than 90 degrees in this case, in terms of the bond angle. So 6 electron pairs and 5 bonds gives us a square pyramidal type of shape. Any question on those? I would say, once again, most people cannot visualize a three-dimensional space, myself included. So learning the number of electron pairs and bonds and the names of the geometries that go with it is probably the best approach for most people. And here's a table similar to one in your book that does that. Again, bonding and electron pairs are geometries that are happening. Also, if you go on Canvas in the exam 2 module towards the bottom of it, it will say like geometry and polarity updated. That's a big list of all the geometries and stuff that we just talked about. That is, again, probably the best way for everybody to remember it is just bite the bullet, electron pairs, bonds, the names that go with those guys is probably the best approach. Any questions on that there? All right, we're laid up there